Benoît Valéron, Shane Mansfield, Alex Kissinger. When we accepted to organize this, we were expecting to do this in Paris, of course, but I had in mind that maybe we'd be more flexible about people attending and try and have a low carbon emission conference format. Now, I didn't expect this. This is a really low carbon emission conference format. So I must thank a number of sponsors: INRIA, Atos, Quantphi, CQC. I thank them for securing us money that in the end we didn't actually need due to the circumstances, but it's always nice to have a net. We were helped into this new conference format by very gifted guys, the tech kids, the so-called tech kids: Matthew Wilson, John van de Wettering, Agustin Bolnia, who is hosting this this talk, Dong-Ho Lee, Kostya Chardonnay, Vladimir Zamskiev. So they've really been doing the technical organization in an amazing way. Well, we'll see how it goes. So today it's a pleasure to welcome Lídia del Rio, who is a researcher at ETH Zurich. She will present us some work with joint with Matthew Pussy and Bettina Meyer on contextuality without access to a tomographically complete set. So let's listen to her. Don't forget that you're strongly encouraged to text out questions in the Slack channel that is dedicated to the talk, so that I can then read them out loud at the end of the talk. Cheers, and let's listen to Lídia.
Thank you, Pablo, and thank you, Pablo, Shane, Alex, and John for organizing and for having me here. So let's see how this goes as the first talk, and which is a live talk. And I try to stick to the guidelines and keep it relatively short, very short. So this is joint work with Matt Pusey, who is now in New York, and Bettina Meyer, who's in the Niels Bohr Institute in Copenhagen. And it's on the archive there. So I'll give you first just an overview of what the summary is. So it's about contextuality, which, as I imagine most of you know, but maybe some don't. It's a way to certify non-classicality of single systems that are compatible with quantum mechanics. And so far, all the formalism for proofs of contextuality, oh, sorry about the typo, they assume that we know at least the dimension of the systems measured. So the original Kochen-Specker once assumed that we know that quantum theory is correct, and Specker's contextuality relaxes his assumption, but still says that we should know how big it is, the system that we're measuring. And this is expressed as saying that we have access to a tomographically complete set of measurements and preparations. I will explain what this is later on. And so we will first tell you that this assumption is not operational. We'll give some examples. And then we show that we can relax it. So we build some tolerance for a number of unknown dimensions, but it comes at the cost of having to make many more experiments. Right? So the complexity of your experiment will grow, for now, exponentially on the number of unknown dimensions. Yeah. Solely from the beginning. Okay, so how do we talk about non-classicality in a world that is compatible with statistics of quantum mechanics when you make an experiment? And I'll start with Bell non-locality, and I'll give the Kochen-Speckers for comparison. So in Bell non-locality, you have space-like separated parties, and the assumptions of Bell theorems are just that you are free to choose the measurements. Each of these parties is free to choose the measurements, which means their choice of measurement isn't correlated with whatever other physics relevant to the experiment, and that they are non-signaling. And this comes via another theory, which is special relativity, right? So you could say that is an assumption that is kind of independent quantum theory. And then the thing that we want to disprove, which is a hidden variable model that is local realistic. So with these assumptions, one builds inequalities, and then how does one show that quantum theories or that reality does not satisfy these three assumptions is by making an experiment, which of course is inspired by quantum theory. Of course, we think we are creating a quantum state, but we don't depend on it. What we need to take for granted is special relativity to ensure this non-signaling, and free randomness, some free randomness in the choice of measurements. In contrast, Kochen-Specker and contextuality, and I'll just recap the simplest example that is not a quantum example, just to give an idea of what it is. And this is the idea of, you have the Specker example. We have 3 boxes, okay, which might be either empty or have a gem inside when you open them. But you can only open 2 at a time. And whenever you open 2, you always find that one is empty and one has a gem. So you always find this anti-correlated outcomes. And the edges here indicate compatible measurements. So you cannot, there's no assignment of states of the boxes before they're open that is compatible with this, with the measurement outcomes, right? That's the idea. So the idea of contextuality is this, that there's no assignment of variables such that for all compatible measurements, the things would be decided before the measurements, and are classical in this way. So the advantage is that you only need a single system to be probed. But originally, this assumes the correctness of quantum theory, that is, that things are described by quantum states. And then the thing that we try to violate, disprove, is this deterministic non-contextual hidden variable model, which means that the statistics of each measurement are independent of the context, meaning of what are the things you can measure at the same time. So this has some problems. The first one is that the experiment doesn't really add much, because one of the assumptions is that quantum theory is correct. Okay. So it's not like in the case of Bell's theorem, in which case you could just make an experiment even without assuming quantum theory, right? The other problem is that the experiments must be noiseless for this to work out. So then comes Rob Speckens and his idea of contextuality. Again, you have a single system, but you have an operationally defined setting, in which we'll talk about later. And the one assumption that he makes, which is not that quantum theory is known, is again that this dimension of the system is known. And he has another way of defining non-contextuality, which implies the Kochen-Specker ones and implies Bell non-locality in the special case, which is that operational equivalence implies an ontological one. And we will, again, explain this later in the talk. So here you can make a violation of this. You can find a violation of the inequalities that are derived from these assumptions through an experiment that's compatible with quantum theory, but does not need to assume quantum theory, exactly like in Bell's case now. And this is more noise tolerant. But what we need to assume is that we know a tomographically complete setup. So we know the dimensions of the system that we are probing. Okay, so let me just recap the operational approach. So we have an experiment that is a special formalism for them. You can think of them as really boxes with buttons that we press, and each button corresponds to a different preparation. And later on, we'll also be able to make mixers, probabilistic mixers of these preparations, meaning I'm not sure if I pressed preparation 1 or 2 with some probability sampled from a distribution. Good. And so then we have a probabilistic measurement for the outcomes, which looks like this. So this is the causal structure. The preparations and measurements are independent. And then the outcomes are taken from this set Km. And according to some probability distribution that we call probability E for empirical or experimental of some outcome K given a preparation and a measurement. And because I said before, we can pick one of these preparations at random. So this means that we can pick them from some probability distribution. We have a local source of randomness that tell us which distribution to prepare, and we don't look. Okay, so this is the model. With this model, then the probability of getting a certain outcome is the average, the weighted average over all possible preparations that are compatible with this probability distribution that we picked. Right. So this is just very standard, and we've not talked about any formalism yet. So then what is a tomographically complete set of measurements? So this would be a set of measurements such that for all preparations and all other measurements, the statistics of these measurements can be derived just from the initial set. So I'll put the formula here, and then I'll give an example that will make it clear. The example is, for example, if you have a qubit, then measuring Pauli X, Y, or Z, knowing the statistics for this measurement for any state can give you, allows you to, by just a linear transformation, to know the statistics for any other measurement. Okay, so, and that's exactly what's written here. So there exists a set MC, this is the complete set of measurements. Function, which is a linear function, such that if you want to know the statistics of getting an outcome for one of these new measurements, then these are linear dependent on the statistics of our tomographically complete set. So essentially, like in quantum theory, it would be that this forms a basis for the space. So how is this assumption different from non-signaling Bell's theorem? It feels like a very natural assumption, but it can fail in several ways. So one that's very natural is if there's some noise in your experiment. There's some hidden degrees of freedom. You think you're addressing just one photon, but in fact, there's some vibrational degrees of freedom, or there is another photon coupled to it, which means that you only prepared you tested some measurements, but in fact, your preparations address more than the degrees of freedom that are tested by these two measurements, which means that if you had an extra measurement later on, it could kind of lift some equivalences. The other one would be that your theory might be incomplete. If you're using quantum theory, then the reality could be a post-quantum theory that has more dimensions that you're not testing at the moment, and which could allow for a non-contextual model later on. We'll see this. So an example would be this example that I have here. No, sorry. An example would be, so suppose you only know on a qubit, you only know the X and Z measurement, okay, and linear combinations thereof. So you only have access to this slice, the real bit, this slice of the Bulk sphere. Okay, so then you might think that preparations that actually prepare, for example, the plus Y and minus Y state are equivalent, but they're not. And there is an extra measurement for the same system, which would be like the measurement in the Y direction, which would tell you, which would allow you to distinguish these two distributions, these two preparations. Yeah. Yes. So in general, this is not an operational assumption. It's not something that we can test, because we can never know if there could be more measurements that address the same system that would show some difference. Okay. So let's continue with Specken's contextuality. So now we derive the concept of operational equivalence. So this means I take two distributions over preparations. So we'll talk only about preparation contextuality. I take two distributions over preparations, and we say that they are operational equivalent if they cannot be distinguished by any of the measurements that we defined as our experiment. So this means that for all the measurements and outcomes, the probabilities, the statistics for these two mixes of preparations are the same. So one example would be in a qubit, for example, to make a uniform mixture over any basis. So it doesn't matter if I'm mixing 0 or 1 with equal probabilities or plus or minus. There is no measurement in the qubits that would distinguish these two things because they have the same density matrix in this case. Right? And of course, it suffices to check all the measurements from our tomographically complete set. So here's the idea. So this could be, for example, this case of mixing. So we have a few preparations. There. We have a few preparations, and we have like two mixers of preparations. Okay, so P1 and P4, you could think of this as preparing state 0 or 1, and P3 and P2, you can think of it as mixing either mixing plus and minus. And let me just show you here again. What's in the axis is the probabilities of getting, so these are binary outcomes, of getting outcome 0 for measurement 1. And in the y-axis, you have the probability of all these preparations into a plane. So what's the problem? The problem is that if you have an unknown measurement, this corresponds to adding an extra dimension, which could lift this operational equivalence. Right? There we go. So here we added this measurement M3, and now it turns out that M3 gives different statistics for all these preparations. Okay? And in particular, these two mixtures now can be distinguished by the measurements. So they were operationally equivalent before, but they are no longer operationally equivalent. So an example would be this thing that we said before, that this extra measurement suddenly measures in the y direction of a qubit. Okay, so we can now distinguish these two cases. Okay. So the next step, so far everything has been just operational, just things we can test in a lab. The next step will be now to build the ontological model behind it. And the idea is that there's an underlying state space, lambda, that is determined by the preparation. Okay? So we have the preparation P, and the preparation prepares some probabilistic mixture of the states, right? Okay. So maybe, for example, I press my button that should prepare a photon in state up, but it can actually prepare something within an epsilon ball of up. Or it could be another hidden variable model that is more than quantum mechanical. And we don't forget that we can still sample the probability distributions for the preparations. And now this probability here at the end, is given by is a theoretical probability of getting some outcome, given that the state that we had, the actual ontological ontic state, is lambda, and the measurement m. So then the empirical statistics are given by this model, and they are exactly like this, right? So you just have to first sum over all the preparations, which we assume is a finite set, and then take the integral or the sum, depending on whether you have a continuous or discrete model, over all the ontic states of the theoretical probability. Okay. So then what is the assumption of non-contextuality? So let's first see what this operational equivalence means for the model. So it means, remember, we had two probability distributions over preparations, is Q and Q dash. And now we just write again what we said that the statistics are equivalent for all measurements. And now we just write down what the model means. Okay, so far we just rewrote what we had before. So this is the operational equivalence. And non-contextuality is this logical jump that says that, okay, if you have an operational equivalence, then we have an ontological equivalence, which means that, which means what's written here, right? That, so not, we have this equivalence not just for any measurement, but in general. So, and the intuition behind it is this idea that if you cannot measure any difference in any way, then it makes no sense that this difference is physically encoded. If it cannot be measured, then it cannot be encoded. Okay, so how does one? So this is Specken's non-contextuality, which implies the usual Kochen-Specker one. Kochen-Specker one. Okay, so how does one from here prove in an experiment then that reality is contextual? So you take these two things. You take this last equality, say that is equivalent to the previous equality, and we build some. Use this in the same sense as with Bell case. We use this to build inequalities, and then we go to an experimental setting and we try to violate these inequalities with the quantum experiment. Okay, so first we need to think about our experiment and think about the system that we're actually measuring and find a tomographically complete set of measurements for the experiment. We find the operational equivalences in most cases. So we find mixtures of preparations such that the statistics match for all these measurements, or for the measurements that we can perform. And sometimes you need two mixtures, but sometimes you need many more operational equivalences. And then you check that these statistics just violate the inequalities. And if they violate inequalities, then the experiment does not admit a non-contextual model. Simple. So in this paper, they've done this in a way that's robust against noise in measurements and noise in the preparations, which is very nice. So what's the problem is that we need to assume that we know the dimension of the system measured. Okay? And knowing this, then we can trust, because we trust that we know the dimension, then we trust that our operational equivalences are really equivalent. And as we saw, if for some reason the physics of the experiment are not what we think they are, we have not seen everything about the experiment, then these operational equivalences can be lifted. Okay. There you go, if we had unknown measurements. Okay, which leads us to Donald Rumsfeld, who says, okay, so there are known knowns, which are the things that we know, which in this case will be the target preparations and measurements, so the measurements and preparations that we know. There are also known unknowns. Okay, so these are things that we know that we do not know. In the case of that we saw before, the only thing that we knew that we might not know is like exactly how the noise affected, and the experiment was robust against this. But then there's also these unknown unknowns, which are the things that we don't know. So, which in this case would be statistics of unknown measurements of a system. Mm-hmm. And the protocol, that proof of contextuality, is robust against known unknowns, but not against this unknown measurements. So our contribution is essentially to add here to the known unknowns, to things that we can prepare against, a number of unknown measurements. So we'll build proofs of contextuality that are robust against some number of unknown measurements. Okay, and So what's left that we cannot prepare against, this will be further unknown measurements. And the goal is to make kind of a comfortable enough buffer of known unknowns. Okay. So our results are several types of bounds. I will not go into the proof, so I'll just state what the results are. So let's start with a proof of contextuality that uses n preparations and m non-binary measurements, which are in the tomographically complete set. So if all these preparations are essential, then adding just one new unknown measurement, so we can have a construction for one unknown measurement, one new direction that allows for a non-contextual model, therefore invalidating the proof of contextuality. Sorry about my autocorrect, correcting all contextualities to contextually. So on the other hand, if now independently of the number of preparations, if the total number of measurements in the tomographically complete set, so known plus unknowns, is exponential on the known ones, then there is again a non-contextual model. So these are the bad news. And this, I'll tell in a bit. So let me tell the good news first. So now we take the case of a qubit, which means we don't have to assume quantum mechanics, but we take a model as compatible with the statistics of a qubit. To make at least 2 to the m preparations and measurements, okay, which are not tomographically complete, of course, these measurements, because it's a qubit, right? You have 3 tomographically complete measurements, and then you add some more measurements for redundancy. You add an exponential number of those. Then, in order to break this, then you need at least m tomographically complete measurements in the non-contextual model. So we have 2 to the m known measurements, but they're not all linearly independent. And this protects this. If we choose them correctly, then this protects against m tomographically complete measurements and against m dimensions, which is not great because it's still an exponential cost. So we have a more economical proof for the simplest case, which I'll just say in a minute. And then we have an algorithm to find proofs of contextuality if the number of preparations is larger than the dimension of the actual tomographically complete set. Okay, so to be robust against this, this algorithm finds, first, it's not efficient. Second, it finds sufficient conditions when it works. And we don't know about necessary. So let me just say, as much as I'll say about the proofs, is that these two and this are done by constructive examples. So the first two are very simple examples you can see in the paper, and the second one needs a bit more thought and gives some insight into the general case. The qubit case is based on Hardy's excess baggage lemma, which is massaged a bit and made stronger. And this algorithm is based on geometry arguments, so in particular character theory arguments, where the idea is that we just build so much redundancy, we just add so many operational equivalences that adding a finite, like a small number of new dimensions would not leave them all, or would still leave some of these operational equivalences. Okay, so I'll just tell you what the simplest case is. This is a maths paper. In the original scenario, you needed only 2 binary measurements and 4 preparations, which corresponded again to this real bit that we saw before. And now if you want to make it robust against 1 unknown measurement, then you need to add 1 more preparation, and you need to add 1 more known measurement that is linearly dependent on the other 2. So that's roughly the idea. And with the catch that we don't really know what this preparation is going to be. So we add one more preparation, but we don't know which preparation exactly, which mixture of preparations will be the one that features in the final proof of contextuality, because this will depend on the dimension of on the direction of the new measurement. But the idea is that because we have enough of these extremal points, then it doesn't matter which direction it will go, there will be one way to catch it in an operational equivalence. So I really don't want to say more about this, so I'll just conclude with what the main conclusion is. So we know that these extra dimensions could be a problem. We know one way to fix it, but for now, we're still paying an exponential price in non-preparations and measurements to make it robust against unknown measurements. So this is the conclusion. And for the questions would be, first, can we close this gap? Can you find more efficient protocols in general, or is it just for the simplest case? Are there more efficient conditions for other or not? And can we make it more noise tolerant, because we have one proof that is slightly noise tolerant, but not by a lot. And finally, like this algorithm, first of all, it's not very efficient. Can we make it more efficient? And second, it gives us sufficient conditions for contextuality, which it might find or not, but we don't know if these conditions are necessary, so it would be nice to work on this. Okay. So, yes, this is all. This is all, Pablo. Hi.
I'm just switching on my mic.
Oh, sorry. Let me go back here.
So thank you very much for the talk. I need to find the clap icon in my...
Does Cisco also have?
Okay, others are doing it. Right. So we have one question from the audience by Shane, which goes back to the idea of dimension. I think he wants to make that a bit more precise. So I'll read it out loud. A couple of questions. So not used that way. Okay. To what does dimension refer here? The quantum system or the ontological model of the system or something else? Okay. And a sub question is, if it's the dimension of the quantum system, then how could one apply Specken's version of contextuality to non-quantum data? Well, I can repeat that later. But,
yeah, the second question is not necessary, because the answer to the first question is that it's at the operational level. So this means that the actual set of tomographically complete measurements is larger than we thought. Has one more element than we thought, and this means one more dimension. So this is a number of linearly independent measurements that allow us to distinguish the different distributions of preparations. So it's all at the operational level, right? He does not assume that it is quantum theory, even though the examples I gave were from quantum theory.
Okay. It does assume some that it is some linear algebraic theory, though. Or...
I mean, things still need to be convex, so in that sense, they are linear.
Okay.
But it's really, because that's the thing, right? Like this function that is here, this fm, this is a linear function, so that all the probabilities work out nicely in the end.
Right. I see.
Right. But it
Okay.
depends on preparations and measurements and not on the underlying model.
Maybe I can try to ask a question, although this is not particularly my field. So if I try to summarize like the main idea in very rough words, it seems that okay, if I well, I've got a set of measurements and preparations and probability distributions that I can do over them. Okay, non-contextuality tells me that I can associate a state to that. Okay, that's what it means. Okay, but then you're saying, okay, but what if you forgot some measurements there? Like maybe there is a room next to the known room, there is an unknown room, and you don't know anything about it, and then therefore you cannot associate any state to that, right? So okay, so and then somehow you're saying you seem to be saying, well, but if I know exponentially well my known room, somehow I can still associate a state, even though I don't know what's in the unknown room. I mean, there is something that
yeah, that's it, but the other way around. That's the main idea, but it's more like I cannot associate a state even. So we want to prove contextuality. Non-contextuality is a nice one where you have the underlying state that explains the measurement statistics. And we want to prove contextuality. And yeah, it's this idea, like, even if I don't know what's in the other room, as long as the other room is small enough, I cannot assign this state. I cannot assign this non-contextual model to the whole thing. Yes.
okay, I see. Okay, that clarifies it.
Was it? Okay.
No, I think so, because yes, you're using it the other way around. Yes, that's good.
Yes, but that's the idea. Yes.
Okay. So we have a question here from Fabio Costa. Isn't it always possible to build a non-contextual measurement that distinguishes all contexts, i.e. a measurement whose outcome tells which settings you choose?
Oh, right. I mean, if you, okay, if you want to be, let me just go to the results. Okay, yes, sure. If you want your model to include like my hand going and touching the button, right? Touching the button that says probability preparation 1 or preparation 2, then of course you get a trivial non-contextual model. Yes, you can always do this, right? But the idea is that now we forget about this and we focus only on the system at hand. Of course, you can always make it so large as to include like even your memory of what you did, and then you always find a trivial non-contextual model. Yes, but the idea is to say, well, now we study just the physics of the system that was affected. Right? In the same way, like you don't need to go all the way to the buttons, but if I use a laser to touch some photons and I keep track of this laser, then of course I can create like a trivial non-contextual model. Yes. Yeah.
Okay, another question by Wong Xian Yu. Could you be more specific about the contextuality algorithm? Are you referring to the complexity classes related to Arthur Merlin or interactive proof systems?
This is a very, very informal statement. We just refer to the time it takes to run in our computers. So I would love to make it more, to make these arguments about complexity of the algorithm more precise. At the moment, we just have something that works and that we know is slow. Yes, but you can find it on the paper, and you can study this, and it will be very welcome. Yes, if you don't do it, then I will.
Okay, let me see if this is another question. Right. So I don't know whether this is a question or a comment. I'll just read it. Okay. So that's from Shane. So okay. So if I try to translate this back to something more familiar to me, I'd take GPTs as a kind of ontological model in which, in particular, we have convexity, linearity, as Pablo mentioned on the live call here. Is this a fair way to think of it?
Yes, I feel like there's a follow-up question to that, but yes, you take GPTs, take the preparations and the measurements as defining your GPT. Yes.
Okay. So there's no follow-up question.
Oh, there's no
yet.
follow-up. Oh, there's not a trick question. Okay. Yes,
If
but
if you can guess it, you can answer it.
no. No, but yeah, that's the way to see it, is the GPT. I mean, the idea of GPT is also to make things more operational, just have preparations and measurement. Yeah.
Right. So so then, okay, Fabio comments that GPT is not an ontological model. Then we have
It's the
Eric
operational model, right?
Vacanti saying that an ontological model is more than that. It's more akin to a classical causal model.
So what I meant is that this is like the operational model, not the ontological one. Sorry, that GPTs are more like the operational model.
Okay. Okay, because Shane was saying that I take GPTs as a kind of ontological model.
Sorry. Yes, that's not. Yeah. Sorry, I heard wrong.
Okay, right.
So you take GPTs as your operational model, and then you take something else to explain them. Yes.
Okay, right. Well, I think you did pretty well as a first experience of this live talk with Slack questions. I must thank you warmly, and I found it very interesting.
Thank you.
And so I think that our super tech can cut it off maybe.
Okay.
And I'm allowed to clap physically, so I'll do it.
Nice. Okay. So,